In this lesson, we'll do two things to wrap up the unit. We're going to take a look at combined input and output, or combined horizontal and vertical transformations, and then we'll also take a look at inverse functions. So, in example 2, you'll notice that we have two transformations happening to a related function. We have a 2 times 2 on the outside, and we have an x plus 3 on the inside of the function. We'll need 4 columns for our table of values. So we'll need x plus 3, f of x plus 3, and then finally 2 times f of x plus 3. This time our original function or parent function points will go in the middle 2 columns. Wherever we see input and f of that same input, that's going to be where the original points will go. So our original points for this function are -3, 0, -1, -2. Notice we're skipping over -2 because there's no turning point in the function there. That is, it just keeps going in the same direction along the same line. Now we have 0, 0, 1, 2, 2, 0, 3, -3, and 4, -2. We can go either direction with this. We can take care of the input transformation first or the output transformation first. It doesn't really matter. So in order to go from x to x plus 3, we have to add 3. So if we're going in the opposite direction, we have the x plus 3's and we want the x's, we're going to subtract 3. So -3 minus 3, -1 minus 3, 0 minus 3, 1 minus 3, 2 minus 3, 3 minus 3, and 4 minus 3. And then in our last column, we'll take 2 times the f of x plus 3 values. So we're going to double each of these. And now our first and last columns in the table of values give us the transformed x, y pairs. So we have -6, 0, -4, -4, -3, 0. So here's what we have so far. -2, 4, -1, 0. This is that curved part of the graph. And then 0, -6. Line segment to connect those two, and 1, -4, and a line segment to connect those two. So you can see we have a translation left 3 and also a vertical stretch. Let's take a look at B, y equals -f of 1/2 x. We can also do a table of values on this one. X, 1/2 x, f of 1/2 x, and finally the opposite of f of 1/2 x. The original points will go in those middle columns, -3, 0, -1, -2, 0, 0, 1, 2, 3, -3, and 4, -2. To go from 1/2 x to x, we'll double or multiply by 2. Sorry for the lousy handwriting there. So we are doubling, and then to go from f of 1/2 x to the opposite of f of 1/2 x, we're just going to take the opposite or multiply by -1. first and last columns are the xy pairs for the transformed graph. -6, 0, -2, +2, 0, 0. Well, let me fix that last point. That should have been -2, 2, and now 0, 0. That looks better. And now we have 2, -2, 6, 3, so 6, 3, and 8, 2. And you'll probably notice at this point that I must have forgotten a point in my original parent function. So I think we forgot one here in between x equals 1 and x equals 3. So let's put that in there right now. The point that I forgot, I believe, was the point 2, 0. If we take the opposite of the y value, that's 0. And if we double the x value, that's 4. So we're missing the point 4, 0. That looks better. And now we can see a horizontally stretched and vertically flipped graph. All right, let's take a look at f of the absolute value of x plus 3. So we need x, absolute value of x, f of the absolute value of x, and then finally f of the absolute value of x plus 3. And so our parent function points are going in the second and third columns. Let me make sure that I get them all this time. -3, 0, -1, -2, 0, 0, 1, 2, 2, 0, 3, -3, and 4, -2. All right, now let's do the tricky one first. It's easy to take the absolute value of x, but when we're undoing it, we have to think about solving the equation. The absolute value of x is equal to 4. What is x? And that would be plus or minus 4. Same idea for 3 and for 2 and for 1. When the absolute value of x is equal to 0, x can only be 0. When the absolute value of x is -1, there is no possible x value, nor can the absolute value of x be equal to -3. All right, now let's actually just go ahead and draw a line through those two entries where we don't have x values because they won't produce anything on the graph. Now we're going to take the y values and we're going to add 3 to them. So 3, 5, 3, 0, and 1. So now we have highlighting here. First and last columns, those are our xy pairs for the transformed function. We have 0, 3. And then we have plus or minus 1, 5. So that's 1, 5, and also -1, 5. We have plus or minus 2, 3, which is 2, 3, and -2, 3. So thinking about the right part of the graph, that's that same oval shaped, like a half of an oval, or whatever you want to call that curve. And then the left side is producing that exact same oval. All right, now where did we leave off? Plus or minus 3, 0. So 3, 0 and -3, 0. And plus or minus 4, 1. So 4, 1 and -4, 1. You notice that we get something that's moved up 3, but the right side of the graph is only moved up 3. Nothing else has happened to it. The left side of the graph was wiped out and replaced with a reflection of the right. That's what that absolute value of x transformation as the input does. All right, let's check out this one. This one will be interesting. What I want to make sure that I think about in this one is that we have f of negative x plus 3. So instead of thinking 3 minus x, it'll be easier if we think of this as multiplying x by negative 1 and then adding 3. So now let's make our table of values. We have x, we have negative x plus 3, f of negative x plus 3, and the absolute value of f of negative x plus 3. All right, parent function points go in the middle columns. Negative 3, 0, negative 1, negative 2, 0, 0, 1, 2, 2, 0, 3, negative 3, and 4, comma, negative 2. All right, let's think about those inputs first, because that's probably going to be our hardest thing to do. We have 2 inputs there, two input transformations to worry about here. So if I'm going from x to negative x plus 3, I'm going to 1 multiply by negative 1 and 2 add 3. So if I'm going in the opposite direction, that is, I have the negative x plus 3 value and I want to figure out who x is, we're going to undo those operations in the reverse order. So 1, I'm going to undo the add 3, which is subtract 3. And then secondly, I'm going to divide by negative 1. Okay, let's take care of those x values first. So in order to go from the negative x plus 3 value to the x value, we'll have to subtract 3 and then divide by negative 1. So negative 3 minus 3 is negative 6. Divided by negative 1 is the opposite value. And then negative 1 minus 3 is negative 4, and we'll take the opposite. 0 minus 3 is negative 3. Take the opposite of that. 1 minus 3 is negative 2. Take the opposite of that. 2 minus 3 is negative 1. Take its opposite. 3 minus 3 is 0, and the opposite of 0 is 0. 4 minus 3 is 1, and then we need to take its opposite. All right, the y values are always easier because we're going forward for those. So we're just going to take the absolute value of each of the y values in the original function, which means we shouldn't have any negative y values. First and last columns are our x and y pairs for the transformed function. So we have 6, comma 0, 4, comma 2, and 3, comma 0. Oops, need to graph that one right. 3, comma 0. What you'll notice is this is kind of from the left part of the graph, right? Because we did take opposites when we figured out what the x values were. So that means that we're going to do some sort of horizontal flip here. Left will be interchanged with right. All right, now let's keep going. We left off at 3, comma 0. Now 2, comma 2. And 1, comma 0. That's the next part of the graph, which is that curved shape. And then 0, comma 3. and -1, 2. And that's that last part of the graph. So what happened to us here? Looks like our left got interchanged with right. It moved over a bit, and then all the stuff that was below the x-axis got reflected above the x-axis. Stuff that was already above stayed above. Okay, now let's talk about what an inverse function is. The inverse of a function is produced by interchanging our x values with our y values. A relation, which is another way to say an equation that relates x and y, or a graph that relates x and y. So a relation and its inverse may not necessarily be functions. Recall that a function has only one output or y value for each input or x values, and it must pass the vertical line test. So in example 2 here, the graph of a function is given. We are supposed to determine if its inverse is, we're supposed to graph its inverse first, and then determine if that inverse is also a function. So let's make a table of values for the function. The function has as xy pairs -2, -3. Looks like 0, 1/2. 2, actually, there was one missing from this table of values. Let's put that extra one, or actually there's one missing point that's kind of should be noted on the graph. Should be down here. No, that's not true, actually. Sorry, not missing. All right, so we have -2, 3, 0, 1/2, 2, 1, 4, 1.5, and 6, 5. So if I'm graphing the inverse, all I need to do is interchange those x and y values. And then just graph. -3, -2. 1/2, 0, 1, 2, 1 and 1/2, 4, and 5, 6. When we connect these, what you'll notice is that the graph is sort of pointing in a different direction. The ends were going kind of straight up and down, and now the ends are going kind of left and right, more than straight up and down. Some observations, aside from that we just interchange the x's and the y values, there is a symmetry about this graph. If I were to draw a line straight through in a diagonal, in fact, the line y equals x, the two graphs would be symmetrical about that line. So, is the red graph, the new graph that we drew, a function? And the answer is yes, because it would pass the vertical line test. If you pass a vertical line through that graph, it would intersect in no more than one point at a time. All right, let's do the same thing for this next one. Let's graph the function first, or rather, let's create a table of values for the function first. So it looks like we have -5, 3, -3, 2, 1, -1, 1, 1, 0, 3, 1, 5, 2. So when we're creating its inverse, we're going to swap the x and the y values. And that'll create a new table of values for that inverse. And then let's just graph those ordered pairs. So we have 3, -5. 2, -3, 1, -1, 0, 1, 1, 3, and 2, 5. So this V shape is now a sideways V shape. Again, observation, if I were to draw the line y equals x, that would cut right down the middle, and each graph would be a reflection of the other over that line. Now this time, if I were to pass a vertical line through the inverse function that we just drew, it would intersect in more than one point, meaning there's more than one y value associated with each x value in some cases. So in this case, our inverse is not a function. In our first example, the inverse was a function. All right, now let's see how that works with equations. If I'm going to write an equation that is an inverse, then we're going to need to use inverse function notation. Now you'll remember the inverse function notation from when we did inverse sine. So in inverse functions, it looks like an f with a -1 exponent and then the of x. And it's read f inverse of x. However, that -1 is not an exponent. It denotes an inverse, so it's not the same thing as 1 over f, for instance. As far as notationally, be careful that -1 superscript needs to go after f and before of x. So in order to create an inverse equation for a one-to-one function, and we're not going to worry about what constitutes a one-to-one function, that's for a later discussion, we're going to first replace f of x or whichever other function we have with y. So let's do that in example 3 below. We're going to replace g of x with y. Second step, we're going to interchange x and y to create that inverse, because that's what an inverse is. You just interchange x and y. Now we're going to solve this equation for y. We can do that by, let's clear fractions first. 3x equals y minus 6. And then y is equal to 3x plus 6. And finally, last step, but it's still an important step, solving for y is not the end. We're going to replace y with the inverse of the function we originally started with. I started to replace it with f inverse, but then I remembered that the original function is g, so the inverse function should be called g inverse. So there's our final answer. G inverse of x is equal to 3x plus 6. All right, your turn to try B. F of x equals 5x plus 35. Find the inverse. And pause the video to do this. All right, here's the answer for B. F inverse of x is equal to 1/5 x plus 7. So a couple things. Did you remember to distribute the division by 5 to both terms? Secondly, did you remember to replace y with f inverse? That's an important step. There is an equivalent answer you could have given, and that would be f inverse of x is equal to x minus 35 over 5. And you could have left it like that. Since both terms were not divisible by 5, you can leave it in that form if you wish. All right, let's do an example for a cubic function. So h of x is equal to 2 times the cube root of x plus 1 plus 3. So we're going to start by replacing the h of x with a y. And then we're going to interchange x and y because that's what creates the inverse. And now we're going to solve, whoops, I don't think I replaced the x with a y. Let me fix that. Now we're going to solve the equation for y. Now we also want to think about order of operations here. Think about what you would do if you plugged in a y value. If we plugged in a y value, we'd add 1, take the cube root, times 2, and then plus 3. That means that when we're solving for y, the plus 3 has to be the first to go. So we'll start with subtracting 3 from both sides. And then divide by 2. You can distribute that division or not. So if we divide by 2, now we need to undo the cube root. That'll be done by cubing. So x minus 3 over 2 cubed. Now, a quick word about the cubing here. Number 1, you can leave it in the form x minus 3 cubed over 2, or x minus 3 over 2, the quantity cubed. And secondly, if you choose to cube it, remember you'd have to multiply x minus 3 over 2 times x minus 3 over 2 times x minus 3 over 2. You cannot just distribute the cubing. So safe, just don't do it. All right, lastly, we're going to subtract 1, and I'm going to skip a step here, and I'm going to subtract 1 at the same time that I'm replacing the y value with h inverse of x. So h inverse of x is equal to x minus 3 over 2 quantity cubed minus 1. Remember that the -1 superscript goes after the h and before the of x. All right, let's move over to D, and this is your turn to try one on your own. Pause the video while you do this. Here is the answer. This is our inverse for a cubic function, which was a cube root function. Again, did you remember that to replace y with p inverse of x, and when you write p inverse of x, make sure that the -1 superscript goes after the p and before the of x. All right, now let's take a look at a different type of function. Now we're going to look at a rational function, polynomial in the numerator and in the denominator. I'm going to do two steps at once. I'm going to replace k of x with y and also interchange the x and the y values. So x equals y over 2y minus 6. In this case, x appears in two different places, and so we need to replace both of those with y's. When we're working with a rational function, you will want to clear the denominator first. So multiply both sides by 2y minus 6. Distribute. And now you'll notice that we have two terms with y in them. I'm going to move the two terms with y to the same side of the equation, subtract y from the right side of the equation, and add 6x to from the left side and move it to the right. Once we get that, you'll need to factor out the y from the left side of the equation. That gives us 2x minus 1. And now divide. And at the same time that I'm dividing, since I'll have solved for y, I'm going to replace that y with k inverse of x. So k inverse of x is equal to 6x over 2x minus 1. And that's our final answer for the inverse function. That necessary step of factoring out the variable that you're solving for if it appears in multiple terms. We did that when we solved equations for polar functions sometimes. All right, here's one for you to try on your very own. Pause the video while you do this one. All right, here is the inverse function. Quick reminder, did you remember to replace y with f inverse of x? Secondly, did you remember that the superscript -1 goes after the f and before the of x? Thirdly, there is an alternate answer that you could have that is equally valid. If you had written f inverse of x is equal to -5x over x minus 2, your answer would be correct and it'd be the same as mine. It just looks a little bit different. Remember that when you have fractions And for instance, if I have a fraction 3 over 5, rather negative 3 over 5, that's the same as the fraction tongue-tied here. Negative 3 over 5 is the same as the fraction 3 over negative 5. That is to say, if both numerator and denominator are opposites, then our fractions are the same. All right, so moving on. The next thing that we're going to do is to show that two functions are inverses of one another by finding their compositions. So two functions are said to be inverses as long as f of f inverse of x is equal to x, and f inverse of f of x is also equal to x. Note that actually finding the inverse is not the same as showing that the two functions that we already have are inverses. So whenever it says show that two functions are inverses, it doesn't mean find the inverse and say, yeah, I got the same thing. What it means is we want to find the compositions of those two functions. So these functions, even though they're not named as inverse functions, we're asked to show that they are inverse functions. So let's start with the composition g of f of x. So g of f of x is equal to 3 times f of x plus 2. Right? G of x is 3x plus 2, so g of f of x is 3f of x plus 2. All right, let's keep going with that inverse. F of x is the function x minus 2 over 3. And what you can see here is that the multiplication and division by 3 are going to undo one another. And we're left with x minus 2, and then I'm going to bring down that plus 2, and that gives us x. That's good. And a function and its inverse should undo one another. That means if you plug in x, and then you plug that result into the inverse, it's going to undo what you just did and give you back the same x value that you started with. All right, let's check out the next one, which is f of g of x. So f of g of x, and I'll sort of color code that here as well, f of g of x is equal to g of x minus 2 over 3. F of x is x minus 2 over 3. F of g of x is g of x minus 2 over 3. Now let's take a look at what g of x is. G of x is the function 3x plus 2. Bring down that minus 2 and the over 3. We can combine like terms in the numerator, and we get 3x over 3, and that gives us a final result of x. And so that's just a check to see if those two are inverses. They both gave me a composition equal to x. Remember that we have to do both compositions. All right, now last example here, show that these functions are inverses, and these are rational functions, so it's going to be a little bit more complicated algebra. So let's start with p of h of x, and p of h of x is h of x over h of x minus 2. In other words, we replace all the x's in the function p with h of x's. Okay, now let's replace h of x. H of x is the function 2x over x minus 1. Let me center that a little bit better. And now let's remember some clever algebra that we learned on how to simplify complex fractions. That is, we're going to multiply the numerator and the denominator of this function by x minus 1. All right, there's only one fraction to multiply in the numerator, and that's going to cancel out our denominator, so that's just going to give us a 2x in the numerator. Downstairs, we have a binomial. We have to distribute to the fraction first, and that's going to give us a result of 2x minus, and then distribute to the 2 after the minus sign. So 2 times x minus 1, no canceling there. So upstairs we have 2x, downstairs we have 2x, and distributing minus 2x plus 2, and that's just going to give us 2x over 2, which yields x. That's what we were looking for. All right, now let's check out the other composition. For the other composition, we have h of p of x. So h of p of x is equal to 2 times p of x over p of x minus 1. All right, so we have 2 times x over x minus 2. Downstairs, x over x minus 2 minus 1. All right, let's scoot that over a little bit. Let's simplify the numerator first. Remember that when you multiply a fraction times a whole number, that multiplication multiplies into the numerator only, not the denominator. So 2x over x minus 2. Downstairs, x over x minus 2 minus 1. Now we'll have to simplify this complex fraction by multiplying the numerator and denominator through by x minus 2. Upstairs, that's going to give us 2x. Downstairs, x minus x minus 2. So we have 2x over x minus x plus 2. And that is equal to 2x over 2, which is equal to x. Check. Those two are inverses of one another. And that's it for the lesson.